In our last video, we talked about how magnetic fields don't ever do work on moving charges. They cause a change in direction, but not a change in speed. And that might sound familiar to you from an earlier chapter. Let's consider now the path that these particles will follow as they go through a magnetic field, and then we'll see how that relates back to something we talked about a little while back. So for the first one, let's say that we have a positive charge, and it's moving in this direction, and it's going to go through this magnetic field that all points into the board, and it's a uniform magnetic field, so that means it's the same strength all the way around here. Okay, so our charge enters our magnetic field, moving to the right. Now our force that's going to be acting on this charge, we can figure out with the right-hand rule. So point your finger in the direction of the velocity vector, and I'm realizing I need to start this a little bit lower to be able to show it well. So this is a positive charge moving this way. Enter the magnetic field. As soon as we get into the magnetic field, our force is going to be, here's our velocity vector. Our B field is pointing into the board, so middle finger needs to point into the board like this. And then our thumb is going to point in the direction of the force on this. So if this is moving to the right and it feels a force upward, it's going to start to curve upward. And I'm going to go ahead and extend this a little bit so we can follow the path, assuming that it's completely constant here. So let me change this up a little bit. Okay, so our starting velocity, and it starts to curve upward. And so at some point there, it's moving straight up. And now our velocity vector has changed. That's going to affect the direction of the force. So our velocity vector now is upward, our pointer finger upward. Middle finger goes in the direction of the magnetic field, so that'd be into the board like this. And then our thumb will point in the direction of the force. That's to the left now. So our charge is going to curve over to the left. Now at this point, our particle is moving to the left. The magnetic field is still into the board, so middle finger goes into the board, and thumb points downward, and we have a force downward on this thing, so it starts to curve downward. And then down here, we have our velocity vector down, our magnetic field vector is into the board, well, that's kind of a tough one to do, and then our force is going to point to the right, and so our particle starts curving to the right. And it's going to repeat this process. We have circular motion when this happens, uniform circular motion because it's not changing speed. Remember, there's no work being done on this, so it can't change speed. So circular motion through this. If we have a different orientation of the magnetic field or the starting velocity, that can change what orientation our circle is going to be in, but it's always going to be circular motion. At least it's going to be circular motion in one dimension or in two dimensions. We might also have some motion out of the board or into the board. So let's say instead of just going to the right initially, our charge starts out going to the right, and it has some component that's out of the board. So this component that's out of the board is, it turns out, not going to be affected by this magnetic field. So if you try and do this one with your fingers, be careful, you're going to hurt yourself doing this one. We find that our velocity vector, part of it anyway, is pointing in this direction. Magnetic field, that's the middle finger, that needs to point back this way. Well, you'll notice that I can't really do that with your fingers. That's okay. You don't need to be able to do that with your fingers. The force, remember, is the magnitude of the force is equal to QVB times the sine of the angle between V and B. If we have our velocity vector this way and our magnetic field vector in this direction, that angle is 180 degrees. So our force, because of that part of our velocity, part of the velocity that comes out of the board, is equal to 0. So what that means is that the component of the velocity that's parallel to the magnetic field doesn't change. It doesn't change direction in that dimension. So if our particle starts out moving kind of this direction, both to the right and out of the board, this magnetic field is going to cause it to move around in a circle like this, but it's also moving outward toward the camera or away from the board. So instead of just doing this motion on the board, it's going to do this motion but continue to move outward from the board. So we get a spiral or a helix in that case. Now, how big a circle would we get here? That's learning target 143. How big a circle would this be? Well, we can figure that out by going back to our circular motion stuff. So we said the net force in the centripetal direction has to be equal to mvt squared over r. And here I'm going to go back to the case where we had no outward component of the velocity, but it doesn't change anything if we have that. That isn't affected by this. Our force toward the center of the circle is that force from the magnetic field. We call that the B force, or the magnetic force. So that'd be FB is mvt squared over r. We know direction here, so we don't need to worry about doing the cross product here. We can just have the magnitude in now. So the magnitude of that B force is QFB times the sine of the angle, which in this case, since we're looking at a velocity that's perpendicular to our magnetic field, it's going to be 90 degrees, so we'll just have times 1 is equal to mv squared over r. We'll have one factor of our v cancel and multiply r to the other side, so we have r qb equals mv. And so the radius of this circle is mv over qb. And that q, I'll go ahead and put an absolute value around it, just use a positive number. If it's a negative down there, all that's going to, we get a negative radius, which doesn't make a lot of sense for us. All it would do would cause the charge to be moving in the opposite direction. So instead of going around in a circle like this, it'd go around in a circle like this. But the radius would be exactly the same. So let's go ahead and use just an absolute value there. So radius of that circle depends on the mass of the particle, how fast we shoot it through this magnetic field, how strong the magnetic field is, and how charged that particle is.